Hi everyone, sorry about the power outage today, but I wanted to go over my notes with you on the kinetics of nuclear decay and first order exponential decay and work a couple of problems so you'll get caught up. Okay, so this is the equation of first order exponential decay, which says that the rate of decay is equal to some constant times the number of atoms that are present at time t. This is a differential equation where the change in t is change in n is dependent on n, and the solution to that equation is nt equals n0 e to the minus kt, where k is a constant, t is time, n0 is the atoms present initially, and nt is the atoms present at any given time. If you were to plot that equation, it starts out at n0 at time equals 0 and decays away to nt along the line here at time t. You can rearrange this equation, nt over n0 equals e to the minus kt, and then taking the natural log of both sides, you get ln of nt over n0 equals minus kt. And this is the equation that we'll be using for the half-life problems. And in those problems, they'll mention something about percent remaining or percent decayed, and you have to translate that value that's given into this expression right here, nt over n0. Once you know that, you can calculate the time it takes for that to happen. Okay, so nt over n0 is the ratio of the amount remaining divided by the initial amount. It's different than the amount that has decayed, so you want to try to keep that straight. Okay, half-life of something is the time required for half of the number of atoms to decay. So therefore nt over n0 equals 0.5. And if we stick that into our equation, we get natural log of 1/2 equals minus kt. Now this is the time it takes for half to decay, so we call it the half-life. And then you simplify by saying that k equals ln of 2 over t1/2 equals 0.693 over t1/2, and then t1/2 equals 0.693 over k. So in a problem, if they give you the half-life and you need k, you can solve it with this equation. And if they give you k and you need the half-life, you can solve it with this equation. So an example problem, which is shown in the lecture slides, is you have plutonium-239. They give you a half-life of 24,100 years. How long will it take to decrease to 1% of the original value? So what that means is 0.1% of the original amount is the same as 0.1% remaining. It's not the amount that's lost. That would be 99.9%. The amount remaining is 0.1%. So that is 0.001, and that equals nt over n0. So we simply stick that into our formula, take the natural log of 0.001, and you can see that k is equal to 0.693 over the half-life, and we get a value of t, which is 240,000 years. Natural log of 0.001 divided by the k value, that is the time it takes to decay to 0.1% of its original value. Okay, now that is a type of problem is in contrast with the other type of problem, which I call a rate of decay problem. That was a half-life problem. This is a rate of decay problem, and this one is from homework number 6, problem 5, where americium-241 decays into neptunium-237 and gives off an alpha particle. Now notice the stoichiometry here. We have 1 mole of each of these, okay, or the molar ratios are the same. And we also need to recognize that the rate of decay of americium-241 is also the production rate of the alpha particles. So every time an americium disappears, it produces 1 alpha particle. And so the question is asking to find the rate of decay. Rate equals k times n. K is this familiar 0.693 over the half-life. The half-life was given in the problem, I believe. And yes, it was. And n is the mass of americium-241 converted into moles and to number of atoms. Okay, so we solve for k, first of all, k being 0.693 over the half-life, and the half-life is given as 433 years. We have to convert that into seconds using this conversion factor. And that gives us a k value of 5.08 times 10 to the minus 11th per second. And in the problem, the particular problem I had, that there was 1.96 grams of americium given, and they want to know what is the decay rate in the first second. So we have to convert this to atoms. We take the molar mass of americium 241. Notice that it's the same as the mass number, multiplied by Avogadro's number to get the number of atoms. And then we can solve for the rate by saying that it's K times N, K being 5.08 times 10 to the minus 11th, and N being 4.9 times 10 to the 21st atoms, gives us 2.41 times 10 to the 11th americium 241 atoms decay in the first second. That is the atoms per time unit of the decay rate. So since that many atoms decay in the first second, that must be how many alpha particles are also produced in the first second.